Hello everyone and welcome to 2026, even though it's the 4th of March. Now what I try to do over a year is try to produce at least one video once a month. That gives me 12 a year. However, it's already the 4th of March and I haven't produced any yet. So if I want to produce, say, 12 videos by New Year 2027, I'll have to produce more than one a month. So we'll see if I can do that. This question is taken from the 2023 Advanced Higher Physics paper produced by the Scottish Qualification Authority. Question number 7. The question is on spectral broadening. Now I could go straight in and do the question, but it's very, very important to know what the background is. Because if you don't know what the background is, there's a danger here, and the big danger is this. You can still do the question, and you might get the question wholly correct. But if you don't know what the proper background was, or you've only got a basic understanding of what the background was, then yes, you've only got really a big idea of what it is you have done, and that can be a bit of a problem. For example, suppose you get a good pass for higher physics or a good pass for advanced higher physics, but you've only got a big understanding of what you've done, because that is possible. That is very, very possible, because I've seen it. So then you go to university, you see, and you present your qualifications, and your university will look at this. That's a very well qualified person. This, I think, will give this person a place. So you get your place at university, but you look much better on paper than you are in fact in reality. So the result of that is you go there and you're unprepared for this course and you struggle, and that is a serious problem and a serious source of misery. And this is the problem that these so-called private tutors create. All they are really doing is making you look better on paper than you actually are. That's what they do. What this video will do is give you the necessary background. But all my videos, in fact, I give you the background, then we'll proceed to the question. So the background to this video is this. What is line spectra, how do you produce it, and what are the necessary measurements that we should take? Once we've done this, we're in a position to proceed with the question. Now this is a diagrammatic representation of how we produce a line spectrum. First of all, we start off with a gas trapped in a tube. And the gas I'll discuss here is hydrogen, because it's the most famous and it's the simplest. Then I have a slit, I have a prism, and I've got a screen. Now when I switch the gas on, the gas will start to glow. That glowing, now as soon as that starts to glow, we say to ourselves, right, there's an energy change taking place here. The atoms that make up the gas are absorbing the electrical energy and producing light energy. So immediately we have an energy change. So we're thinking about energy here. Electrical energy to light energy is the energy change. The glow from the gas will be collected by a slit, which will produce a beam of light. That beam of light will be incident on a prism, and the prism will refract the light or disperse the light, and the amount of the refraction will depend on the frequency of the light. Remember, the higher the frequency, the greater the refraction. The refractive index of a glass block is a function of the frequency of light incident upon it. We can measure the wavelength directly from our apparatus. It's usually a spectroscope, and we can measure angles and we can work out the wavelength. That's for another video. When we worked out the wavelength, we can use frequency is equal to the speed of light divided by that wavelength to give you the frequency. And the speed of light is 3 times 10 to the 8, so 3 times 10 to the 8 divided by the wavelength of the light to give you the frequency, and also to find the energy of the light. Now think of the light in terms of photons, particles of light. So what is the energy of these photons of light? Well, that's given by h times f, where f is the frequency and h is Planck's constant. For example, well, that has got a wavelength of 434 nanometers. 434 times 4 times 10 to the minus 9. To find the frequency of that, we all divide 434 nanometers into 3 times 10 to the 8 meters per second to get a frequency of 6.91 times 10 to the 14 hertz. And the energy of the associated photon, well, that is Planck's constant, 6.63 times 10 to the minus 34, multiplied by 6.91 times 10 to the 14 hertz to give you the energy of the particle of light, to make up that colour as 4.58 times 10 to the minus 19 joules. And those are the important measurements that we need to know. So then, how does an atom produce light energy? And here I'm going to discuss the hydrogen atom because that's the simplest. And that's got one proton in its nucleus and it's got one electron going round and round it. This is a representation here. And if you notice, the orbitals are numbered n equals 1 to n equals 6. These are the allowed orbitals for an electron and an atom. In this case, a hydrogen atom. So, suppose that the atom is relatively cold, and suppose the electron is in the n equals 1 orbital. We say it's in the ground state. But then we give the atom energy from our lamp. We give it energy. The atom will absorb that energy and the electron will jump up to a higher energy state, n equals 2 to n equals 6. When it's in that state, we say it's in the excited state. It's absorbed this energy. It's now a much more energetic atom, and the electron is in a higher energy state. But no sooner is it in that energy state that it falls down to a lower energy state. And as it falls down to a lower energy state, an energy change is taking place. Electrical potential energy of the atom goes to radiated energy as it falls down. So when it falls down from n equals 6, say, to n equals 2, it produces a much higher frequency, much higher energy than, say, if it falls from n equals 3 to n equals 2 that you can see. And here's a wee illustration of that. And you can actually see the higher the energy drop, the greater the frequency of the light. And this is how an atom produces energy. This is how an atom produces light energy and other frequencies of radiation that we cannot see by our eye, but we can nevertheless detect with detectors. And now to the question. Question 7. The emission spectrum from a mercury vapour lamp includes a spectral line corresponding to photons of frequency 1.18 times 10 to the 15 Hz. In practice, the spectral line is produced by photons with a range of frequencies delta f. This results in a spectral line of width delta lambda, as shown in figure 7a. The width of the spectral line can be explained using the Heisenberg Uncertainty Principle. State what is meant by the Heisenberg Uncertainty Principle. Now, in quantum mechanics, we have this very famous and unavoidable principle called the Heisenberg Uncertainty Principle. It's normally stated in terms of position and momentum. For example, suppose we have an electron, because it really only refers to the micro level, the atomic or subatomic level. Suppose we have an electron and we wish to measure its position. Now, measuring the position of anything, we can never ever get anything to zero in accuracy. Everything will have an inaccuracy, but we can always improve it. So if you've got an electron, for example, and we wish to measure its position, that position will have an unavoidable uncertainty. Now, it can be very, very small, it can be a tiny uncertainty, but there will always be something. Similarly, with its momentum, we can measure its momentum to a great degree of accuracy, or a very, very small uncertainty. Where the problem arises, though, is when you try to measure both of them simultaneously. When you measure both of them simultaneously, you come up against a wee bit of a barrier, because the principle states this: the uncertainty in the position, delta x of the electron, multiplied by the uncertainty and the momentum of the electron or tiny particle within the atom, has to be greater or equal to h over 4 pi, where h is Planck's constant. You can't avoid that. No matter how well you measure something, you cannot avoid that. But it basically says this: the more uncertain, the less the uncertainty in the position of the particle, the greater the uncertainty in the momentum, and vice versa. Now, your momentum can have a tiny uncertainty, less than 10 to the minus 34, but this will mean the uncertainty in the position will be correspondingly greater. So if we have got a tiny, 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 tiny uncertainty in the momentum, then we've got no idea where the particle is, and vice versa. And this is how it's expressed: delta x times delta p is equal to h over 4 pi. Now you might be thinking, oh, h, 6.63 times 10 to the minus 34 joule seconds, that's virtually nothing. And it's true, it is, but not when we're talking about subatomic particles that are measured, that have got lengths of nanometers and even sometimes femtometers. You can't ignore it at that level, although you can ignore it when it comes to Newtonian mechanics at the macro level. But for this question, our question, looking at spectral broadening, we use the uncertainty principle again, but not in this form. We use it in the form delta E times delta T is equal to h over 4, where delta E is the uncertainty in the energy of the photon, or in the energy state from which the photon is produced, and delta T is the time the electron or the atom is in its excited state. And the product of those two things has to be greater or equal to h over 4 pi. Part 2. The range of photon frequencies is due to the uncertainty in photon energy delta E. The uncertainty in the photon energy can be determined from the lifetime of the electron delta T in the excited state. The lifetime of the electron in this excited state is 1.2 times 10 to the minus 13 seconds. Determine the minimum uncertainty in the photon energy. 3 marks. So for this question, we start off with our inequality. Delta E times delta T is equal to h over 4 pi, but it's an inequality. So delta E times delta T can be any value, provided it's greater or equal than h over 4 pi. Now, if it happens to be equal to h over 4 pi, then that's the least value it can be. And for this question, we're asked for the least value of delta E, given delta T. Well, so what we do then, we write it as an equation and we put the wee minimum on the delta TE just to make it clear that we understand what we're doing, and we're working out the minimum uncertainty in the energy of the photon or in the energy level, which comes out to be 4.4 times 10 to the minus 22 joules. Again, very, very tiny, but significant at this level. It means when we are drawing our energy levels, n equals 1 to n equals 6, that I did previously in the video, well, we now know, depending on the time the electron is in that energy level, these energy levels are a wee bit blurred. They're not quite as sharp as we thought. They're a wee bit blurred. In this case, the one we're referring to is blurred by 10 to the minus 22 joules times 4. Part 3. Determine the minimum uncertainty and the frequency of the emitted photon. Now for this expression here, we know that E is equal to HF. And we also know that the fractional uncertainties on both sides of the expression have to be the same. So delta E over E is equal to delta F over F. Then what we can do is, we know that E is equal to H times F, rearrange it, and we get delta E is equal to H times delta F. That allows you to find delta F, the uncertainty in the frequency of the emitted photon. That is 6.6 times 10 to the 11 hertz. So if there's an uncertainty in the frequency, because there's an uncertainty in the energy level, there must also be an uncertainty in the wavelength. And that uncertainty in the wavelength represents the width of our spectral line, which is the next question. The width of the spectral line can be calculated using the relationship delta lambda is equal to C delta F over F squared, where the symbols have their usual meanings. Calculate the width of the spectral line. And finally we arrive at our destination, finding the width of our spectral line. And for that we're given a wee formula. Delta lambda is equal to C delta F over F squared. Where do you think that formula came from? Well, it came from C is equal to F lambda. C is a constant, so the fractional uncertainty in F has to be equal to the fractional uncertainty in lambda. Which means delta F over F is equal to delta lambda over lambda. If you put in lambda is equal to C over F, substitute it in, you'll arrive at that formula. When we put the values in, we get 0.14 nanometers. And that is the width of the spectral line, or the broadening of the spectral line, due to the Heisenberg Uncertainty Principle, where there is always an unavoidable inherent uncertainty in how we measure, especially at the subatomic level.